This is part 2 of section 9.1. We're still trying to estimate something about the population. We're still trying to estimate some proportion that the population has. You know, what percent of people will never wear green socks again? That kind of thing. Something we're interested in estimating about the population. So last time we looked at just the mechanical way of actually doing a confidence interval. It's very mechanical. You're just plugging numbers into a formula, basically. This time we're going to go into it in a little more depth. Well, you'll see when we get into it here. So this is still section 9.1. So I used this little graphic last time. The green thing is our net, if you will, our confidence interval. And we're hoping that somewhere in there, the population parameter is trapped, is captured. We don't know if it is or not, but we want to just make a guess. And just like last time, p hat is dead center in our interval. Anybody remember where p hat comes from? Okay. Yeah, from our sample. So we get a sample, we get p hat, and that's right in the middle of our interval. Now, we didn't really bring up a whole lot about margin of error. And notice we've got a margin of error on either side of p hat. That's what makes up our net. Those two sides are equal. So if I've got 3% margin of error on the left, I've got 3% margin of error on the right. It's symmetric. So another way of looking at it is, if you tell me the margin of error, I can tell you how wide that interval is. So if the margin of error is 0.03, I know that my interval is 0.06. If the margin of error is 0.05, then it's 1, right? Just want you to get this picture in your head. And which part is governing the margin of error? Well, this down here. This part of the formula in blue. Now that's part of the formula we looked at last time, right? The only thing missing from it is p hat out there on the left. But the margin of error is plus or minus, then some critical value, that z alpha over 2. And then the rest of it is the standard deviation for proportion. Now that's in your formula pages. You don't have to memorize that. Just realize that this part is the margin of error. That's all I'm saying. Let's look at what a 95% confidence interval is saying, because there's a lot of ways you can make a mistake about this. So if I say I'm 95% confident about something, here's what that really means. That doesn't just mean I have a good feeling. It means this. That if we did this sampling over and over and over, thousands and thousands and thousands of times, that we're going to get a p hat for each one of those samples. And the intervals that we form based on those p hats, 95% of them would actually have the population parameter in that interval. Kind of ironic. This in itself is a proportion. If we did the sampling over and over and over again, 95% of our intervals, somewhere in that interval is the population parameter that we'll never know. We're just trying to guess it. Here's what it's not saying. It's not saying the probability. No, once you see probability, you're wrong. It's not saying the probability that our interval contains that parameter is 95%. No, it's not a probability at all. Remember, probability is always about something that's going to happen in the future. This interval is something we've already done. So think about it like this. If I've got a deck of cards, before I draw a card from that deck of cards, can I talk about probability? Sure. What's the probability I get a king? 1/13 or 4 out of 52. Once I draw the card and I lay it down on the table, it's either king or it's not. The probability is either 1 or 0 if you're still talking about probability. So just make sure that when you're talking about confidence intervals, what that really does mean. So I do want to show you something. Give me a second. This is in StatCrunch, and that's an app that is actually included in your textbook. It's in the modules. If you go way down in the modules and look, you'll see StatCrunch. And this is one of the applets. So take a look at what's going on. Up here at the top it says, let's assume that the population parameter is 0.5. That's what this is saying right there. And we're going to do a sample of size 50. And I'm going to do that 1,000 times. So I'm going to get 1,000 p-hats. My confidence level is 0.8. So I've got an 80% confidence level. So that's what all those numbers mean. I want you, this picture I think might explain it better than just words can. So I'm going to do 1,000 intervals. I get this. And over here on the left, it's got all the intervals listed and which ones missed and which ones hit. What do I mean by that? Well, the ones in red, notice the little dots in the center? Those are the p-hats. So those red dots represent p-hat, and then the interval is around p-hat. Now the black line going down the middle is 0.5 because that's the population parameter that we really don't know. We're trying to guess it. So if you look out here on the far right, it said of this simulation, a little over 80% actually contained this black line. If you look at it closer, this one right here just barely caught it. Just barely. But it caught it. Some of these are close to dead center where the dots are. Some up here. The ones in red missed entirely. So look at the width of those intervals. Now that's being 80% confident. What would happen if I went to 95% confident? What's going to happen to those intervals? They're going to get bigger. A bigger net is more likely to catch that parameter. So let's do that. Let's go to 95%. They got bigger. Look out on the right, it says 95.6% of them caught that parameter. Again, that black line going down the middle is the parameter. So we're trying to guess. If I sort that out, you can see real easy which ones missed. So all the ones in green, somewhere in them, that black line's running through it. If you look at the green ones down at the very bottom, they just barely caught it, but they caught it. The ones at the top, they just barely caught it, but they caught it. All right, so what if I increase the sample size to 500? What's going to happen? We're going to talk about this in a minute, but what's going to happen? The margin of error is built around the standard deviation. What happens to standard deviation as the sample size goes up? Right? It gets smaller. Yeah. So I'm going to change my sample size to 500. Going to do it over again. Look what happened to the interval width. Got really tiny. So that's what a confidence interval is. It's just you're setting boundaries and you're saying, I think the parameters between here and here. That's all it's doing. Okay, so if you get into StatCrunch, you can play around with that. Okay, let's keep going. You're going to be asked to interpret a confidence interval. It's got 4 parts. So when I'm checking quizzes and stuff, I'm going to look for all 4 parts. Why would you interpret one? You're going to give information to somebody. You just did a study or an experiment or something. You're going to publish your results. And you can do it in 1 sentence. So here's first part. I want to know, what level of confidence are you talking about? Is it 95%? Is it 80%? The lower the level of confidence, the less I'm likely to believe that that parameter's in there. If you tell me I'm 5% confident that the real parameter's in between here and here, I'm going to go, so I don't put much stock in that. Next thing, I want to know, what population are we talking about? The book doesn't spell this out, but I really want you to think about using this form as we're interpreting these intervals. If we're talking about students, is it all the students that are 12th graders at Peaster High School? Is it all students at Peaster High School? Those are 2 different populations. Is it all students in Parker County? Because now we've got several schools involved. Is it all students in Texas? Those are 4 different populations. So tell me which one you're talking about. And be specific. Next thing, what were you trying to figure out in the first place? What's this proportion you're after? Is it what percent of people believe in the Easter Bunny? Is it what percent of people voted independent in the last presidential election? Is it the percent of wild raccoons that have a certain disease? It's not always about people. And then finally, actually show me the interval that you just built. So it's got these 4 parts. They don't have to be in this order, but you can put all of that in 1 sentence. Here's a for instance. And I put them on separate lines just so you could see it easier. I did put these in the order I had up there at the top, but you don't have to, as long as you make sense. So I'm 90% confident. Okay, there's my level of confidence. That the proportion of residents of Parker County. Okay, I just told you my population, the residents of Parker County. That think we should have free ice cream on Friday. Well, that's what I was interested in finding out, right? That's what I'm trying to guess about the residents of Parker County. And then the last thing is, what's my interval? Well, in this case, it's between 23.6% and 31.7%. So in 1 sentence, you can interpret a confidence interval. Could you say that a different way, maybe? It's usually pretty good to lead off with how confident you are. So I'm 90% confident that between 23.6% and 31.7% of the residents of Parker County think we should have free ice cream on Friday. So I can change the order some. It's saying the same thing. But let's let folks know we're talking about a proportion here. Okay, stop right there. Questions about that? So on the next quiz, they're going to say, find a confidence interval and interpret it. Yes, ma'am.
When you meant by miss, what would that be?
That miss, that means that interval put your hands like this. That means there's your interval, and maybe the population parameters out here. Your interval doesn't contain it. That's all it means. We're hoping that it's somewhere in here, because look what I just told people. I'm 90% confident that between this percent and this percent, I think we ought to have free ice cream. What if that's not correct? See, my guess is wrong. Good question. Anybody else? Okay. Let's do one. So we've got a survey of 700 students at community colleges. This is community colleges in general. Out of those 700, 481 said that this past year they saw a UFO. Do what? We won't ask about their mental state at the time. I want to find a confidence interval, a 90% confidence interval, that lets me guess about what percentage of community college students in general have seen the UFO this past year. So all we've got is just our information from our sample. We sampled 700 people and got this result. So the first thing I'm going to do is find p hat. So how do we do that? Well, it's just 481 divided by 700. It's just a fraction, just a percent. And I'm just going to change that to a decimal number because that's going to work out so much better. So 3 decimal places is fine to take these out too. Get your formula pages out. And you don't have to, that's figuratively saying. And plug these numbers in. So this formula is in your formula pages. So notice what I'm doing. I've got p hat plus or minus 1.645. Now wait a minute. Where'd that 1.645 come from? You remember? Right. From that little table. That little table says, well, if you want to be 90% confident, then that 1.645 has to go right there. That's that critical value based on our confidence level. If we were talking about 95% confidence, that would change to what, 1.96? Claire, are you seeing where that table is? If you look at the table with the z-scores, it's down at the bottom. And it gives you just the most common ones. And so the last thing on the right, this radical, is just what? Standard deviation. So I'm just going to get the calculator and plug those values in. Okay, I'm with you. Put them in order though, because we're talking about an interval. So start with the left-hand side and go to the right-hand side. So same interval, right? That's mechanical. There's no great thought that goes into that. You're just plugging numbers in. So I need a volunteer to interpret this for me. Elijah, you want to give it a shot?
I am 90% confident that the students at community colleges have seen a UFO this past year. Or that the people, the students have seen a UFO in the past year is between 65.8% and 71.6%.
That's it. I'm 90% confident that the proportion of community college students who've seen a UFO this past year is between 65.8% and 71.6%. Now that's a guess, right? It's based on one sample. It's a guess. We know that if we did the same sampling over and over and over and over and over again, thousands and thousands of times, that 95% of the time we would be correct. Our interval would contain the parameter. All those intervals are going to be different because they're all based on different samples, like we saw in that little graphic from StatCrunch. But for this sample, this is what we're thinking. Okay, we good? Here's a general statement. The more confident I am, the wider that interval is. Or I could turn around. The wider the interval is, the more confident I am that population parameter that I'll never know is actually in my interval. All those intervals we saw in that graphic a few minutes ago, when they pretend like each one of those was a study. In each one of those studies, they didn't know if they actually captured the parameter or not. The red ones didn't. Would the people know whether they did or not? If this one back here is really true, we're 90% confident, but do we know that that's true? No, we don't. We never will. We're making a guess. That's what statistics does. It makes a guess. As best of a guess as we can, based on math principles. And what did this leave out? Were these randomly chosen students? Doesn't say. If they weren't, then none of this makes any sense. All right, let's keep going. So in blue here is the part of the formula that governs margin of error. The only thing left from that formula is p hat sitting out there on the left-hand side. It's not there. That stuff in blue is the margin of error. We know as my confidence level goes up, the margin of error gets bigger on each side of p hat. And that z alpha over 2 is that critical number that determines how big that part of the formula is. The thing I've got circled, if we're talking about 90% confident, that value is 1.645. If I'm talking about 95% confident, that's 1.96, so it just got bigger. What's happening to that whole side there? It's getting bigger because I'm multiplying by a bigger number. If I go to 99% confidence, then we're talking about what? 2.575? Just got a lot bigger. So 99% confident means I've got a great big net I'm throwing out there. And here's my question. And this is something we couldn't get into last time. Is there a way I want to be high confidence but have a small margin of error? Because a great big margin of error doesn't do anybody any good. If I told you I'm looking for somebody, I'm pretty sure they're between California and New Jersey. Okay. Not much good information there. So are 350 million other people, basically. I want to narrow down that margin of error so I've got something useful, a useful guess. Is there a way to do that? So here's the question. Can I keep the same confidence level, say at 95%, but make the net shrink? Peyton says, yeah. How, Peyton?
Did you increase the sample size?
Good. Excellent. Look over here. If n gets bigger, what happens to that fraction right there? As n gets bigger, what happens to that fraction? It gets smaller. So I could keep this confidence level the same, and this part of my fraction is getting smaller, so what's that doing to the margin of error? It's making it smaller. And so by manipulating n, you can say ahead of time, before you ever do the study, I want to be within plus or minus 0.03. I want to be within 0.02. Because you need to know the margin of error. All right, so just like the lady said, make n bigger. Because if you do, the margin of error goes down, even with the same level of confidence. That's the cool part. You can still be 95% confident with a smaller margin. Much more useful. Well, that sounds pretty easy, right? Just make n bigger. But I want to know ahead of time my margin of error. As it turns out, this is in your formula pages. This formula, they took that standard deviation thing coupled with the critical value, and they just worked it backwards to find out what size n would you need to get a certain margin of error. So look what it's saying. Take p hat, multiply times 1 minus p hat, and then you're taking your critical value up there on top as the numerator and dividing by the margin of error, and then you're squaring that. That's not going to be very big, that margin of error on the bottom. But since that's small, what's that going to do to the fraction? Make it big. Anybody see a problem with this? This looks great on paper. Okay, let's pretend we're starting off. I want to be within 3% on either side as my margin of error. How many people do I need? What was that? A lot? Yeah, possibly. Let's get a little more detailed. Yeah. Look what we're using in there. We're looking for the sample size, but we're basing it on what? P hat? Have we even done this study yet? No. Where's P hat coming from? P hat we get after we take the sample. So this is like a catch-22 kind of thing. I need to know how big my sample has to be, but to compute that, I need to know P hat. Well, that P hat in that formula right there is sort of, think of it as a placeholder kind of thing almost. So since we don't know the true P hat yet from our sample, since we haven't even done the sample, I'm going to pick one of these choices down here at the bottom. Either I'm going to have some previous study or previous data that gave me a version of P hat before I'm ever doing my study. Sometimes those are called pilot studies, where you'll do a small study just to get an idea of what's going on, then you'll do the big study. Now, if I don't have something like that, I'm just going to use 0.5. One of those two things, and in a question on a quiz, they might ask you both ways. The homework probably will. But the formula is there. All right, so let's look at one. All right, this economist hasn't done her survey yet, but she knows ahead of time she wants to be within 3 percentage points on either side. She wants a margin of error of 0.03. How many people does she need to survey? Well, now in this case, part A, we've got this census data that says, oh, 64%. Now that might not be what she's going to find now, but in 2020, that was the case. So she can use that as her dummy P hat, if you will. So let's plug that in. Notice I'm using 0.64 from the previous data. You already got it? Hold on to it just for a second. See what you get. Okay, Elijah, what'd you come up with? 1,697.44. Okay, like that. Now, great. I mean, we're either both right or we're both wrong. Here's what you do. Always add 1. Unless that comes out exactly 1647, always add 1. Because I want to be within that margin of error. We're not rounding, Because if I rounded that, that'd be 1647, right? I'm sorry. Yeah, 1647. 97. Can't read from the back of the room. 1697. We're not rounding. We're just adding one.
And we're always
What if we didn't have that? Like part B here. And expect this kind of thing on the homework and on the quiz. They'll ask you, well, if you had this, what would the sample size be? Or on the other hand, if you did not have that prior information, what would it be? So now what are we going to do? Well, we're going to use that 0.5. So instead of 0.64, I'm using 0.5. Elijah, what you getting?
Yeah, 1,841.84, but 1,000.2. 842.
All right, thank you, sir. We add one. We're not rounding, we're adding one. And somebody asked last class, well, why don't you just use 0.5 all the time? Which was a great question. Why not? Let's look at this. What was the sample size? 1698. What's the sample size using 0.5? 1842. That jumped up, what, 140 or so. If you use 0.5, you're always going to get the biggest sample. If you use 0.5, you're always going to get the biggest sample. Well, what's wrong with that? Ma'am? Maybe I don't need that big a sample. That's one reason. What if it cost me $100 each person I interview? Now we're talking about money because these samples cost money. So for 140-something people, $100 each, what does that come out to be? $14,000 or something? Am I thinking that right? So money is an issue. If I don't need those extra people, like the lady says, why get them? We only use 0.5 when we don't have something else to base it on. Stop right there. Questions? So look what we looked at. Margin of error. I hope that makes sense. I hope you have in your mind a picture of what a confidence interval looks like. We saw a bunch of them in that little simulation. How do you decide how big a sample to get? That sort of thing. So based on what we did last class time and today, that's section 9.1. Tomorrow, we just spent 2 days talking about confidence intervals based on proportions. What do you think we're going to hit tomorrow? Not proportions, otherwise known as averages, means. So we can have a confidence interval based about an average. It's going to work very similar to this. We're not going to have to talk about the theory of it because you already know the theory of it. If you look in your formula pages, the formulas are different. That's one of the big differences. So